we have the fourth lecture by Xiaoming Mao, and okay, let's go.
Okay, yeah. It's my pleasure to give the last lecture for the school, and thank you all for staying until now. So the lecture today, I think, is going to be more or less a random walk through many slides, because I'm not sure what's the best order, so I will be guided by the reaction of all of you. So to start, I would like to just really start from some reviewing a little bit of back the basic concepts, right? So just to remind you, we defined the Q and the C matrices, which I assume you all at this point understand very well. And they are transposed to one another. And you can construct the dynamical matrix. And I think the concept we mainly are going to use is that the null space of the C matrix, I think here. The null space of the C matrix here are all of the zero modes, right? So if you have a vector where C dot this vector is 0, it is a 0 mode. And the null space of the Q matrix are states of self-stress. If you have a vector of bound tension that causes no net force on any side, it's a self-stress. And then you apply rank nullity theorem on these two matrices. You apply it to Q matrix, the rank, which is the number of non-zero eigenvalues, plus the dimension of its null space is the number of its columns. And you can do the same for C matrix, and because they have the same rank, you get this so-called Maxwell-Calladan theorem, which I think Corentin explained already in his lecture. So then, I think, let me see. These slides, yeah. These we mostly go through, just want to show another example. So here, if you look at this structure, right, as a mechanical frame, there is 1, 0. There are 4 zero modes. 3 of them are trivial zero modes of the translation and the rotation of the whole thing. The fourth one is this non-zero one we call a mechanism or a flopping mode. In this case, you add one more bond, you kill that one, it becomes isostatic. Isostatic refers to that you have no states of self-stress, nor zero modes, nor flopping modes. You can still have zero modes depending on the boundary condition, right? And here I just want to show you this other example where you add 4 more constraints by pin this point and this point, okay? So when you do this, how many, I guess the answer is already there, but you can still think, right? How many zero modes and the states of self-stress are there compared to this case? So here, you still have 3 zero modes, right? But in this case, is it clear why I call this 4 more constraints? Because each point, when I pin it, I fix both the x and the y, right? So each of these pins are 2 constraints. And then as a result, I remove all of the zero mode and give the system 1 constraint, give the system 1 state of self-stress. And then, yeah, this defines the Maxwell point. And then I think the only new thing I would like to mention is actually this equation. So for a system, one of the importance of defining these states of self-stress is that you can use that as a linear space to map out all of the possible load a system could carry. So here I made another example where I add 1 more pin, so 2 more constraints, right? So remember, before I added the last pin, I have 1 state of self-stress. So that is the only way when the system can become stressed. But now I add 1 more pin, I have 3 states of self-stress, right? You can numerically calculate it, 3 states of self-stress. And these are the only ways the system can become stressed. And what this equation does is that when you have an external load, which means in this case, you put external forces on these 3 pins, right? You can stretch them in some way. And you can always project that to all of the states of self-stress. And this equation very conveniently tells you what the stress distribution in the material is going to be, okay? And then just to finish this part, I would like to mention another new paper we wrote. I forgot to add the reference, but anyway, it's our work on pre-stressed elasticity, and we propose that you can still do this Q and C matrices when the system has pre-stress on it. And basically, you can write the elastic energy as a part of the central force stretching of the bonds, and add another term that comes from the fact that the bond carries tension or compression already. And in fact, this coefficient can be either positive or negative, because when it carries compression, it wants to become unstable, right? It wants to have transverse motion. So you could have negative coefficient here. But as long as the whole matrix add up is positive definite, the system is still stable, okay? And then you can still define Q matrices, but now the dimension is larger when the system is pre-stressed. And here I just give one example of we take a triangular lattice. So you know triangular lattice is over-constrained. You can have many states of self-stress on it. Here we just excite a random state of self-stress on a triangular lattice. And then we ask, when we put this pre-stressed triangular lattice under shear, what is going to be the reaction of the system, right? So here we show, using this method, you can really quickly calculate what is the mechanical response of the network. So here we need to use 3 colors because each of the bond now can not only carry increment of the longitudinal tension, but it can also carry a reaction to the rotational component of the stress. So the notation is better determined, is better explained in the paper, but here just to give you a picture. So what we show here is that this formulation don't require the system to be conservative. You can have non-conservative interactions, which you can just conveniently put in the rules for this tension, right? And then as a result, you can use that to describe non-conserved systems. For example, here what we did is that we say, because this particle is compressed so much, it broke, right? For example, it crashed. If you imagine it's a granular system, then locally the stress is released here, but you can, without changing anything, you just change the coefficients here, you can calculate its response. Or if we imagine it has some kind of active response, so that the particle actually grows bigger when you compress it, you can still use this projection to predict what is the response of the linear response of the system. Okay? So it provides a convenient tool. So that's this part. Any questions here? Okay, so we are going to next go back to our discussion of topological mechanics. So it's still the same set of slides, but I need to navigate to that part. So remember last time we went to, let me see, this slide. Okay, just to recap. Right, so we have Q and C matrices, and follow K and Lubinsky, we constructed this chiral Hamiltonian, where when you calculate the topological winding number, we said that it's going to tell you 0 modes and the states of self-stress. Right? So next, I'm going to spend a little time to explain how does it really work, why this winding number tells you the states of self-stress and the 0 modes on the, at the interface and the boundaries of the system. So it takes a few steps. Firstly, remember that the 0 modes are solutions of this equation, right? We just said. And then for a periodic lattice, you can write this equation in momentum space like this, okay? And then you realize that if we have a Maxolatus, this matrix is a square matrix, right? So what is the condition for a square matrix to have a solution like this? you need to have the determinant to vanish, right? And then you can see that this is a square matrix as a function of k, right? And if you want its determinant to vanish, these are two equations because you have real part and the imaginary part. But if you have only one, if you enforce the k to be a real valued wave vector, in general, there's no solution, right? In general, you need to allow k to be complex in order to determinant c to be to have a solution. And we know that when you have a complex k, that means you have an edge mode, right? So if you have a wave vector that has real and an imaginary part, the real part is the oscillation. The imaginary part is the decay or the growth, and it's a description of an edge mode, right? Then what the important question we need to answer is so this is another line. So say that for a 1D system, you just have 1k, right? You can just solve it. And for a 2D system, what we do is we fix a wave number in the transverse direction, and then we ask what is the solution for the other direction, right? Because this topological index is always describing a one-dimensional localization. So the important question is what determines the sign of the imaginary part of the k? And that can be related to this topological index, okay? Any questions on the relation between these parts? Yes?
When I think about topological edge modes, I usually think about them going around all of the boundary and not just one part. Do you usually just have modes that connect at the corner, or
right, so this is the case of a 1D topological index. So it tells you the localization on one side. And what you describe are the chiral modes for two-dimensional system that goes around. And the Maxolatus is, I think, so far we have not been able to realize that type of modes in this. Any other questions? Okay, so here is we want to know what determines the sign of this solution, right? This turns out to be a question where you can use analytic functions and properties of these integrals to explain. This is a complex slide, so let me do it slowly. I think I probably it's better to do it on Blackboard, but anyway, you can draw a complex plane of this block factor z, okay? The block factor z e to the ika is the factor. So if you look at a linear mode, a linear wave on the lattice, this z is the factor when you go from this lattice site to this unit cell to the next unit cell. What is the factor you multiply, right? And then you go to the complex plane like this, and then this unit circle on this complex plane is a mapping of the first Boolean zone, right? So you change the wave vector k from 0 to 2 pi or from minus pi to pi, right? You go around this unit circle because if this is a real number, if ky is real, this z can only take a mod of 1, right? So you go around this circle. And then you realize that any point in the inside of the circle corresponds to k has an imaginary part that is positive, right? If you put an imaginary part positive here, you will see that the mod of z will be smaller than 1. If you put an imaginary part negative, it will be points outside of the circle, right? Yes?
I know that the relation between the index and the edge at which you have the mode depends on the convention you use for the unit cell.
Yes.
So how does it change then if you change convention for your unit cell? I guess, can you just swap the argument? Or?
Yeah, so we haven't got to that step yet, but it corresponds to how you define your unit cell, which bond and sites you include in the unit cell. That can change the actual value here, but it changes in a way that it shifts for all kinds of lattices. So as long as you calculate the difference of left and right domain around the interface, that one is robust. Okay? So the actual winding number can change with the gauge choice, which is the choice of
But then it
cells.
changes K double prime, right?
Oh, that doesn't change. So this picture is always fine. What changes is actually the pole at the origin. So you get extra poles at origin when you choose different conventions of defining unit cell, which is called the gauge choice. Any other questions? Yes. Yes. It's not the number of poles, it's a singularity at 0 and the infinity changes.
Does that change the Cauchy will change the singularity?
What changes? Yeah.
You're saying that you're changing the singularity?
Yeah, so when you choose unit cell differently, so basically it actually adds factors of z to some power to the determinant of the C matrix. So that changes what is the, I forgot what it's called, like how singular this point and the infinity is.
But you're doing a Cauchy integral, aren't you?
Does that what?
You do a Cauchy integral, which usually depends on the singularity's order.
So it actually, this n depends on it, but n of one domain and n of another domain doesn't depend on it.
Okay.
And actually, we now have a more robust version of defining this winding number where you actually change the contour so that you go around this point. So it's basically, instead of doing the integral like this, you do the integral like this. So then it totally doesn't care about the convention. Yeah, so we have a newer paper where we study continuum elasticity description of this. We talked about this new contour. Okay. Okay, yeah, so here we talked about the sign of the solution. So firstly, the edge modes correspond to 0 points of determinant of C, right? And you care about whether you have solutions inside of the unit cell or outside, inside of the unit circle or outside of the unit circle, okay? And this turns out that you can calculate by doing this integral along the unit circle, because from Cauchy's formula, you know that when you do this integral, it counts the poles of this function. So remember, we want determinant C to be 0, and when you take a logarithm, that gives you a pole, right? So then this formula counts the poles of this inside of the circle. And because this formula, if you look at it, you will realize that it is actually, in another way, also calculating the change of the phase of determinant C as you go around this contour. So as a result, it must be integer valued, right? It can only change by integer times 2 pi. So that tells you that this n can only be integer, and this is the so-called topological protection in this case. And then we can show that when you give the system some disorder, right, it doesn't matter as long as you don't make n to jump to the next value, okay? And this is basically the bulk edge correspondence of Maxwell lattices. Any more questions? So this is the figure from the original K and Lubinsky paper where they show that you can make lattices of different topological states. So here, basically, this is the twisted Kagame. This is twisted Kagame. So these are not polarized. As you can see, these lattices have mirror symmetry, right? It's only that the domain in the middle is polarized in this way. You can calculate a topological polarization. I think I forgot to include that formula. So topological polarization is RT N1 A1 plus N2 A2. Again, there is a gauge choice, and you have to be careful, but roughly, okay? A1 and A2 are the two lattice vectors that span your 2D lattice. And N1 and N2 are the two winding numbers you calculate for the two contours on the Boolean zone corresponding to these two lattice directions. So you have a polarization winding number for first lattice direction and one for the second direction. And this RT is a vector, in general, points to the interface that gains extra modes. Okay? So if you have an infinitely large lattice like this, everything should be perfectly constrained, right? So the number of zero modes and the number of states of self-stress should add up to 0 in the bulk. But the effect of the polarization is that it places zero modes here and the states of self-stress here. Okay? And sometimes we would like to use this analogy with magnetic polarization. You can think of a Maxolatus being topologically polarized like a magnet, right? So you can think of the north pole as the edge with 0 modes and the south pole as the edge without 0 modes. The nice thing is that if you cut it in half, the newly exposed surface will become the new north pole and the south pole because it's a property that comes from the bulk of the lattice. It's nothing special you do on the edge. Okay? And then similarly, if you take pieces of opposite topological polarization and connect it together, you get an accumulation of states of self-stress or 0 modes in the middle. Okay? Any questions? So next, I'm going to just show a number of more recent work we have been doing along these lines. You realizing this in experiments and using these in disordered systems. Okay, so firstly is a work we collaborated with Stefano Gonella's lab. So the question we want to answer is, can these topological flopping modes to actually propagate in space-time, right? So it sounds a little bit non-intuitive because these modes are 0 frequency modes, right? They don't have group velocity. How do you make it propagate? Okay, so it turns out that the fact that these modes are 0 frequency is a property of the idealized bead and spring model. Yes.
Phase velocity, because omega is 0. Do you have symmetry that imposes that also the group velocity has to go to 0?
Yeah, they don't have any velocity, right?
Yeah,
it's a flat line.
Okay, if it's flat then.
Yeah. Yeah. However, the interesting thing is that if you make these lattices to be not a bead and a spring, if you, for example, you 3D print a lattice with a little bit of resistance to bending, that actually lifts up the modes. But nicely, as long as you don't make the bending too hard, the modes are still there. You perturbatively go from this to this. And these branches are localized on the same edge. You have two sets of modes that are localized on the same edge. Okay? And then we can observe that.
Sorry, how do you do that? How you're able to do this transformation?
How do you go from?
How do you do? How do you do the transformation from this relation to how do you make those modes appear?
You add bending, right? That's what you're doing. She's adding bending, and that lifts the modes.
Yeah. So in particular, this is the so-called supercell analysis. So you have a strip of the lattice with periodic boundary condition this way and open boundary top and bottom. So you get many modes, but then you see the edge modes. So then you add a little bit of bending into the lattice. When you redo the numerical calculation, you will see the modes are here.
The bending is only in the center of the lattice, right? I mean, is there bending between unit cells?
Everywhere.
Okay.
It's actually, let me show you the experimental system.
Okay.
So it's a material like this, and this is a picture. So they are bending between all of the triangles. Okay.
Are these
Are these modes still? They are not at a zero frequency
they're
anymore.
a bit, yeah.
Yeah, they are lifted, and it's proportional to the square root of the bending stiffness.
And I guess yesterday I showed that there was also some shear bending. You would have also here some shear bending as well, right? Or you decided not to include it in the
I
description?
think so. Here, actually, yeah, that's a very good question. I think when you consider the connection between these two, right? In what you wrote, this is still free, right? What you penalize are maybe I got it
this
wrong.
Is not free.
No, right. This is bending, and the shear is like this, right?
Yeah.
Yeah, that's right. So I think in our case, this is always costly. And we are now just introducing a small parameter for this. Yeah. Because the idealized model, you just put a bead here. And it's just the spring and the mass model.
So if you wanted shear bending, you would have to make your model a bit more complex,
right.
I guess. Yeah.
Yeah, you have to add other things to make this soft too. Yeah, the two modes are the two, so yeah, I think I skipped something. Let me come back to here. So that's a good question, why there are two modes, right? So if you think about a supercell analysis, right, I just single out one strip of the lattice. There are always supposed to be two modes per transverse wave number. So for each transverse wave number in real space corresponding to one unit cell, right? If you do the counting. And in each unit cell, when you cut this from a periodic boundary condition, you cut two bonds, right? Because if you want to connect this back to the bottom of this lattice, there are two bonds per unit cell that you removed. That gives you two modes. And if you don't make the lattice topologically polarized, if you just have a random geometry, the two modes in general, one on top, one on bottom. It's symmetric. And when you make it topologically polarized, both of them go to the same side. That's a basic counting. Okay? Any more questions? Okay, so now let me describe this experiment a little bit. I think basically they just cut a lattice like this, which is basically of this size, and they fix the left and the right of this lattice and use the laser vibrometry to look at the wave field. They give the lattice a little bit of perturbation from one side and see how the wave propagates in this material. And here is basically what is observed. So remember, this is the lattice, and the floppy modes are all localized on the top. So for each wave vector in the horizontal direction, you get two zero modes, or low frequency modes localized on the top. And the bottom is supposed to be gapped, so you only have those modes in the band, right? So if you send the wave from the bottom, you see that it propagates like in a normal material. It goes into the bulk. But if you send the wave from the top, it propagates along the edge. And the velocity of the wave is determined by how hard it is to bend them. Okay? So you see very different propagation in these lattices as you go in opposite directions. So this is an example of observing soft modes, topologically protected soft modes in these lattices. And next, I'll just talk about like observation of states of self-stress. So usually from the soft matter community, I think we know about the modes much better, right? But how do you use states of self-stress? So this is one example of a paper from Vincenzo Vitali's group. They show that if you I think they 3D print these lattices. If you put state of self-stress between, so you use two different lattice domains, you put it together, there's a state of self-stress. When you compress the lattice, all of the buckling happens in that region. You can pre-program where buckling happens, okay? So then in this work from my group, what we tried to do is to see if we can use this type of idea to control the fracturing of materials. So if you go to the full nonlinear regime and let the material become damaged, what happens? So what we do here is a numerical experiment. We have a 3-domain lattice such that I have a state of self-stress domain wall here and a zero-mode domain wall here. These arrows are the topological polarization, okay? And then I put this lattice under stretch. I just stretch the top and the bottom and see what happens. What we show here is that all of the stress are localized here. And as you may notice, we intentionally put some cracks in the bulk of the lattice. Usually, for normal material, if you have a crack, you will imagine there is a lot of stress localized at the tip of the crack, and that leads to catastrophic failure. Here, using this state of self-stress domain wall, we can protect the bulk of the material from cracks. Okay? And here is one video we generate. So I will pause it a little bit. So we put in a number of, I think, 6 states of self-stress here. And in the middle, there is a really big crack. If you do this to a normal lattice, it's going to crack from here, right, or here. But here, you show that all of the tension goes to these states of self-stress domain walls. And yellow means is just mark the broken bonds. So the damage always first occur at these states of self-stress domain walls. And then if I finish playing the video, you can see that it is only at the very late stage the crack starts to propagate. You can use the domain walls to protect the material. Yes.
Okay. Could you use this to make complex crack path?
Complex what?
Path for crack. Like, could you engineer a complex fracture path?
Complex path. Yeah, maybe. We have not thought about that. So you want to design a particular way that the material crack.
Because you could lay out the topological polarization as you want it, right? So
yeah, I think that's possible. That's a good suggestion. Mm-hmm. So then we went ahead to see whether this actually works experimentally. This is, again, a collaboration with Stefano Gonella's lab. So what we did is now made these lattices with metal. And then here is the state of self-stress domain wall. And they put a strain gauge on a few places in the lattice to test what is the level of stress at these places, okay? And here is the finite element simulation. Basically, we show that when you try to stretch the material, as you can see in the color shows the stress. It is all localized at the state of self-stress domain wall. And other places are protected. And here is the experimental result where you read the strain gauge. You can see that at the state of self-stress domain wall, the stress is really high, and then it quickly decays to other places. The bulk of the material is protected. And then you may say that because in the experiment, we are stretching in a place very close to the domain wall, right? Is that an artifact? They also tried to move the location where they give the lattice the stretch in a different place. And then the stress is still here. It's probably harder to see from far away, but you can look at our preprint here, okay? And then we also showed that really interestingly, you can ask the question, why is this better than like a normal fiber reinforced material, right? So here we say that when you place a state of self-stress domain wall, it attracts the stress, protect other places. But in engineering, people have done for a long time just fiber reinforced materials, right? You can place fibers that carry the stress. How is this any better, right? We can show that, interestingly, it is more robust because of the topological protection. So to test that, we show a contrast experiment, numerical experiment, where here we have the state of self-stress domain wall. Here we just have a normal Kagame lattice, but we have a solid wall here, which plays the role of a fiber reinforcement, right? And then we say that what happens if this domain wall itself is broken because it's so stressed, right? So we put in a crack here. And in this case, you can see that the stress diffuses a little bit, but it still goes back to the domain wall. I think I have a better figure somewhere. No, a better figure maybe is in the preprint. I made these slides this morning. So there is still a lot of stress here, and we have a plot of the level of stress. But in the fiber reinforced material, which does not use topological protection, when the fiber is broken, there's no more stress here. It doesn't help the material at all. So this property comes from the fact that topological protection is from the bulk. As long as most of the bulk is there, it still sends stress to the middle. It doesn't need the domain wall itself to be intact everywhere. Okay? Any questions? Yes?
So when I think of fiber reinforcement, I think of putting in a material which has an ability to bear load.
Yes.
Here, it seems that the ability to bear load is the same. It's just focused there. Is that wrong?
Yeah, I think you can think of it in this way. You can now use much more, you can intentionally use more material at these domain walls. And then you can make the whole thing lightweight by making the bulk much weaker, because now the bulk doesn't do anything.
Okay,
right.
Thank you.
Okay. Okay, so that's this part. I think next I'm going to talk about some recent work we did on using these ideas in aperiodic systems, which is closer to the theme of this school. So why do we want to try that, right? So I think it's a really simple idea that we say topological states are robust, right? They are supposed to be not requiring periodic lattices. So we want to test how this works. And the main difficulty theoretically is that when you don't have a periodic lattices, you don't have momentum space. You cannot do these integrals to define winding numbers. How do you study the phenomena? So we need to find some real space description, right? And in particular, in this series of papers, we developed a real space description for Maxolatus topological polarization. And here I would like to first describe a recent paper we wrote in studying topological polarization in fiber networks. So it's good that Fred already gave a very nice introduction to fiber networks, so I can just start from there. You think of this so-called Mikado network, right, which is a two-dimensional disordered fiber network. And then you can ask, like, what are the floppy modes of this network, right? In particular, we know that the internal nodes have coordination number 4, right? Where if you have an infinitely large fiber network like this, it's supposed to be exactly Maxwell. However, if you have finite size, the nodes that are on the outside of the lattice will have fewer coordination, and that places the whole material slightly below the Maxwell point, so you'll have some floppy modes. And here we drop the bending stiffness. We just assume this is spring mass network to begin with, okay? So let's do the counting a little bit more carefully to know how many zero modes are there and what are they, right? So firstly, the number of degrees of freedom is just counting the number of crossings on the fiber network. You can sum over all of the fibers, and each of the fiber has a number of these crossing points. Right? Each of them has 2 degrees of freedom, but you need to divide it by 2 because each crossing point is counted twice. And then you can also ask how many constraints are there. It turns out to be very similar to this sum, but it's ni minus 1 because if you have n crossing points, you have n minus 1 springs on each fiber. Then you subtract these 2 numbers, you find that the total number of zero modes is the same as the number of fibers. So each fiber carries a zero mode. So what are these zero modes? They are actually pretty easy to map out. So here is one example. You can just take one fiber and pull it to the right. The red arrows are the displacement vectors of the nodes, and the green arrows are their projection to this fiber you are pulling. You can verify very easily it is a zero mode because these red arrows are all proportional to the fibers that are crossing this one you are pulling. So as a result, to leading order theory, it doesn't cost extension or compression. And the green arrows are all of the same length, so it's a zero mode. Okay? Yes?
Xiaoming, you assume that they support compression also?
What?
That these fibers support also compression?
Yes, you just treat it as the normal spring. Okay. Yeah. Any more questions? Okay, so these are the zero modes, and then you can notice that they are all bulk modes, right? There is no decay from the edge to the bulk. Okay, so then what do we mean that we can study topological edge modes in these lattices if all of the modes are just bulk modes? You can realize by comparing 2 periodic lattices that these are exactly analogous to Maxwell lattices, these, like, for example, the Kagame lattice, when you have these lines forming, these bonds forming straight lines. So bonds forming straight lines is actually the topological transition point in these Maxwell lattices. And I can explain that in this figure here. So remember, we talk about Maxwell lattices can have different winding numbers, right? The point when the winding number change are these so-called critical states where you have straight lines. When you have straight lines, they can carry states of self-stress. And that means you can have zero mode in the periodic boundary condition case. That means the zero modes are in the bulk, but by changing the geometry of the lattice a little bit, you can make the zero mode to be either localized on the bottom or localized on the top, okay? And this is basically the idea of this video that I think you saw from Tom's talk, but I'll play it again because it's useful for what we talk about here. So what we did is that we build this lattice using connects. So you have rigid triangles that are connected by free hinges. And in the first part, we show that both of this edge and this edge are soft. You can push it, and the lattice just yield under the pushing. Okay? And by the way, that's Zeb Rocklin. So, but interestingly, the lattice can have a topological transition when you stretch it out. And this stretching doesn't cost elastic energy because it's an intrinsic soft strain, the so-called Guest-Hutchinson mode of the lattice. That's part 2, where you can stretch it out. So in this experiment, we had to put bars here to ensure that when you stretch it out, it keeps being a periodic lattice. But now we have much better ways by introducing bistability to do that. So anyway, you stretch it out, there is a topological transition. After that, as you stretch a little bit, you enter the topologically polarized phase. Now the total number of zero modes are the same, but the distribution of the zero modes are all on the top of the lattice. And the effect you can see in the third part is that this edge, the bottom edge, becomes rigid. It has no soft modes to accommodate the deformation. So when you push it, now the whole thing slides up. It doesn't deform because there are no floppy modes. And it's quite amazing in some sense that these are all free hinges, and then yet this edge becomes an edge that can carry stress. Okay? And the top is floppy.
Xiaoming,
Yes.
can I ask something in
Yes.
general? The main message, you started with the disordered network in this part, and now
Right,
you're talking
so-
about a periodic, yeah.
Right, this is a demonstration using periodic lattice. I'm going to next show how disordered network is going to do that, okay? So the idea here is that in periodic lattices, you can do, you can see that if you follow this deformation, you can manipulate where the floppy modes are. Right? Can we do that in a disordered material? We know that this is exactly analogous to the critical state. So this tells us that you can just perturb it a little bit. Maybe you can then send the floppy mode somewhere you want. Right? It turns out that the way you can do it is quite simple. You just take this fiber and pull it in one way. This is the bulk zero mode, right? We talked about this lattice has bulk zero modes. You just follow this bulk zero mode and pull it a little bit. This defines a new ground state because you follow a zero mode. The stress that is generated is very small. We call it a modified Mikado network. And then we can ask what are the zero modes of the modified Mikado network. We can do a calculation, and then it's nicely exponentially localized on one tip of this fiber that we pulled to the right. It always localizes on the tail. We can use this method to program the softness in this lattice, not in this disordered network. There is no periodicity at all. Okay? So how do we calculate this? This is actually an exact solution. That is the method we introduced to characterize topological polarization in disordered material. So it is a transfer matrix method. I don't want to go into too much detail, just to give you a flavor. So basically, it turns out that we can propagate the solution of zero modes in this lattice node by node. So there are, for example, NF fibers in the network. For each of the fiber, we define a starting point. Then we can propagate the whole solution through the network where we write such a transfer matrix at each of the node. So each of the node takes 2 in, and then 2 out is calculated by this transfer matrix.
Xiaoming,
Yes.
When you do not have the fiber structure, can you still apply this method?
That's a very good question. So sometimes you can. So if all of the sites are 4 coordinated, you can. And we also show that if all of the faces are parallel, if all of the faces are quadrilaterals, you also can. But more general networks, we do not have a solution yet. I think that is one of the work Jose is doing, my student. And we are trying to figure out ways to extend this type of methods to more generic real space networks. Okay? Yes?
I want to make sure I understand. I pull in this direction,
Yeah.
and now I can go back. I guess there is probably still a zero mode exactly in the direction I came, but otherwise there's nothing around me. So
What do you mean?
I pull my fiber network in this direction,
Yes.
and now it's hard here where I've pulled.
That's right. That's right. Yeah.
Yet there must be still a zero mode that is reciprocal to the one I came along. But
That's
it
right.
becomes unique, and only that K vector exactly will take me back.
Yeah, that zero mode is still there. It just exponentially grows to the tail, right?
Or decays there.
Yeah, yeah. It decays to the point you pulled. That's right.
That's beautiful.
Yes, there's a question.
Okay, I was just wondering about the topic. I think it's not a subject about the random vibrations in mechanical engineering. In general, you have a structure. You put around the external stress with a given statistics. The question there is, what is the response, statistical response to the output stress? Linear lattices, let me say. Now, the question, if this question makes sense at all, what's the role of these topological effects on the statistic of the answer when you probe your structure with a random stress with no statistics? Is there something? Is there anything reasonable to answer?
I'm not sure if I completely understood the question. You mean what is the topological effect on the stress?
Yeah,
or
topological effects on the answer, on the vibration of your lattice if you put in a random stress. If you know statistic, if you know precisely the statistic of your random stress, like a bridge over effect of the wind simulated with a given statistic like that.
I see. So like if I take this network, instead of doing this coordinated motion, I just randomly perturb the position of everything, right? Yeah, that is a very good question. So we actually tried that kind of thing in some lattices. What happens is that typically you just get localization on all of the edges. So if you keep everything straight, all of the modes are bulk modes. Everywhere is equally soft. If you perturb, if you just crumple the geometry a little bit, the modes become localized on the edges isotropically. You have to do it in a coherent way so that you have asymmetry, you have a polarization, okay?
So for example, like with the FCC lattice with phantom nodes such that Z
Yeah.
forms.
You mean does it work for FCC? So you have to do it in a smarter way, I suppose, because actually, if you make it Z equal to 6 on every node, then you can use exactly the same method. But that is not, I guess, how fiber networks usually build in 3D. Right? How do you make sure it's always 3 fibers crossing in 3D? Because if it's only 2, then it has too many floppy modes, right? Okay. Oh, there's another question.
If I have a perfect regular lattice, and then I start to disorder, the transition between the disorder and the regular lattice is a continuous transition, or there is an abrupt?
Which lattice?
In between a regular lattice,
lattice.
And a distorted lattice.
So you can define a parameter, for example, the localization length, right? So if the lattice is perfectly regular, the localization, so you mean the critical state, right? The localization length is infinity. Right? Or the decay rate is 0 because it's a bulk mode. But as soon as you start to perturb it, say I introduce a small parameter for perturbation, then the decay rate is this perturbation to some power. It depends on the detail. Sometimes I think it's linear. Yeah, so you get a decay rate that is proportional to how much you perturb.
But it's a continuous transition.
You can call it continuous.
Yeah, I mean, there is no critical point between the...
Right, there's no threshold. The threshold is at 0.
Okay.
Yeah, that's right.
Just one more quick question, Xiaoming here.
Yes, okay.
Is there any hope for an effective medium theory to capture topological polarization?
That's a good question. So I think at some point we thought about that with Tom. So the difficulty is that so far the effective medium theory is using Green's functions, which is inverse of the dynamical matrix. But if you use dynamical matrix, everything is lost. You need to split it into Q and C, right? Or actually, maybe if you use the chiral Hamiltonian, which is the Q and the C on opposite. Yeah, maybe there is a way to do that. Yeah, that's a good point. Yeah. Okay. Okay, yeah, so here is the transfer matrix, which tells you how the zero mode solution propagates. And without the complex math, basically what happens is that if all the fibers are straight, this matrix is just identity matrix because this one becomes this one, and this one becomes this one, if it's straight, okay? But if it's not straight, you can do it perturbatively. You can get a decay factor that depends on how much you bend the fibers at the crossing points. And in particular, there are simple geometries you can map out. Like if I ask how the mode propagates along this fiber, when it bends in this way, and in this way, the mode decays from left to right. And in the opposite case, it grows, okay? And you can show that if you have a large network and you pull this fiber to the right, then on most of the sites, it is decaying. And in the paper, we did a more careful calculation of disorder average and show that you get a positive decay rate. Okay? So that's basically how we can polarize a disordered fiber network in 2D. And then you may ask, like, this seems to be a peculiar thing you do to the network. Does it ever arise naturally, right? When can you expect to actually observe this kind of thing? So we believe that there are a number of systems where this might actually arise naturally. One case is when you have, for example, molecular motors, right? So when you have molecular motors on a fiber network, sometimes it does is that it contracts the fiber, right? Then in this case, the molecular motor will introduce a domain wall where you have a head here and the tail on the outside. And as a result, you get stiffness in the middle, and the mode is large on the outside. When we do the calculation, we find something like it exponentially decays and then grows again, okay? And you can imagine the opposite case, where you have a motor, for some reason, it expands this fiber. Then you get a hard end on the outside and the softness in the middle, okay? And of course, the first order mechanical effect is that it tunes the local stiffness of these points, right? Then there are maybe other interesting effects. For example, it can serve as an amplifier, right? For example, if you put in a motor that contracts locally here, you create a mode that exponentially grows as you go away from this point. Then when you have a small mechanical input here, when you shake here, it's going to excite this mode and create larger signals on the outside of the network. This can serve as an amplifier. And one hypothesis we have is that when you have this in some biological setting, for example, when you have cells on a collagen network, the cells locally exert pulling on the network. And then you may have, so here is one video which I took from this paper, where you can see a bunch of cells, which are the orange dots, that migrate on collagen network. And as you can see that they pull and form these highways for themselves. And we hypothesize that when you form these kind of stressed network, it can serve as also information for them to talk to each other mechanically, okay? So that's this part of recent work we did on extending these ideas to disordered fiber networks. Any questions? Yes.
For this order system, does the floppy mode must be on a straight line? Is that possible to be a bit curvy?
So yeah, so this is a linear decomposition of all of the zero modes, right? So you have a lot of zero modes. The number of zero modes is the same as the number of fibers. So each fiber has such a mode. Here we took a linear decomposition, so they are all degenerate. You can take a decomposition such that you only show this mode, but there are also other modes on other fibers. Those ones are not polarized.
Those.
Right. Okay.
Is that possible to make the polarized mode like a domain wall, which is more complex, like this shape?
Ah, that's interesting. We haven't thought about that. You mean to direct the path of soft modes, right? Yeah, there may be a way to do it if you like coherently deform the fibers in some way. Yeah.
if I take this system, this is order system that I'm sure that have a zero mode. If I calculate the band diagram, this system, can I be sure that this system gonna have a gap? I mean, because if it's the band diagram of the system touch the zero, I mean, can I be sure that always have a gap if I find a zero mode?
Yeah, that's a very good question. It's actually quite complicated to explain. So for 1D system, it's simple, right? If you think about the rotor SSH chain, you have a band diagram like this. And this is the gap, right? That's always clear. Omega versus k, and you have the zero mode down here. For 2D lattices, if you draw it's harder to draw, so you have kx and ky. And by Goldstone theorem, the mode, you always have D mode starting from here, right? So if you draw omega versus kx, the bulk bands always occupy this. We never have complete gap unless you pin the system. So you will have zero modes that come out like this. And if you give it a given ky, then there is a gap. And then you can ask, in the disordered case, what is the gap? Right? That we do not have a good answer yet. I think you can perhaps show it in some way by just calculating the modes in real space, and then say that all of these zero modes are exactly the zero if you don't have bending stiffness, but then all of the other modes, there is a gap. But actually, how large is that gap? How that distant itself from, how other modes distant from this, we have not studied. That's a good question. Okay.
Thank you.
Okay, so that's about the disordered fiber network. So at last, I would like to discuss another recent work we have done in terms of quasicrystals. So how did we get interested in this, right? So we want to see like how does topological polarization interplay with the symmetries of quasicrystals. We know that quasicrystals are these systems which are not periodic, but still has long-range order. Okay? So here is one example of a quasicrystal where you tile the plane with two types of parallelograms. And there is actually a theorem you can show that with these parallelograms, you can tile the whole plane, but there is no way to tile the whole plane periodically. The only way you can do it is aperiodically. And this lattice actually has long-range order. You can show that you can generate this pattern by taking a 5-dimensional hypercubic lattice and cut it with a 2D plane. You can generate it. So it's perfectly ordered. It's just not a periodic order. Okay? So the reason we chose this as our system, this is the so-called Penrose tiling, is that it's actually exactly Maxwell. You can show that the coordination number here ranges everywhere from 3 to 10, but the average is always 4. You can use Euler's equation to show that because all of the faces are 4-sided, the coordination number must be exactly 4. So it's a Maxwell network. So just by looking at this, can you guess what are the zero modes? So firstly, what is the zero mode of one parallelogram? Yeah, you can do the shear of that parallelogram. When you have a tiling of parallelogram like this, can you find the zero mode? how do you squeeze the different parallelograms together? Yeah, it's basically you identify strips of parallelograms, and you have to share them at the same time. So here is one example. For parallelogram tiling, you can always identify this kind of strips by following the parallel edges, okay? And then you can construct zero modes from that, because I can shift the right-hand side relative to the left-hand side. As long as the displacements are all the same on this side and perpendicular to these parallel edges, it's a perfect zero mode, right? Any questions here? So again, as you can see, it's a totally a bulk mode. There's no decay from edge to the bulk, right? So perhaps from the example of the fiber network, you can guess that this is also analogous to the critical state. You can imagine doing something here to also make it polarized. So what is that something you need to do, right? There turns out to be a lot of interesting physics and math here. The way we do it is to use a duality theorem, which uses the so-called reciprocal diagrams. It turns out to be actually proposed by Maxwell when Maxwell first studied this problem. So basically, many of you probably know the concept of dual graph, right? You can take a planar graph, and you can find its dual graph by mapping nodes to face, face to node, and edge to edges. Here, reciprocal diagram is finding the dual graph of a mechanical frame, but you put in the extra requirement that the edges must be perpendicular to one another. The reason we use that is that it turns out these parallelogram tilings and the fiber networks are reciprocal to one another. You can check that by looking at these dots. So for example, if you look at this blue dot, it marks one face in the parallelogram tiling. It maps into this node here. And the four edges surrounding this face maps to the four edges connecting to this dot. And because all of the faces here are parallelograms, that means all of the lines, so each of the strip of the parallelogram turns into a line, and that line must be straight because these are all parallel edges, okay? So it's a very nice mapping, which actually was used in this so-called generalized dual method, where people try to generate all kinds of quasi-crystalline patterns, okay? You can start from a fiber network, which I think was called star vectors and fiber networks of families of parallel equal spaced lines, and then you use that to generate these quasi-crystalline patterns, okay? Any questions? So we are talking about this duality not only because geometrically they are due to one another, but also because there is a theorem tell you that all of the states of self-stress in this network maps to zero modes here. All of the zero modes here maps to state of self-stress here. There is a one-to-one correspondence. So this tells us that if we know how to polarize a fiber network, which we just talked about, right? We can do the corresponding geometric change and also make the parallelogram tiling become topologically polarized. So here I would like to just, I think we still have a little time. I will just explain this reciprocal diagram and this mapping, because I think it's a really interesting theorem that may also be useful for other problems in mechanical networks. So that is actually not too hard to prove, that theorem. So for example, you take a mechanical network like this. Here it's reciprocal network. And to help you see the correspondence, I put labels on the network. For example, I look at this node here, 1, right? It becomes a face here. This node is connected to 3 bonds, 1, 7, 12. they become the bonds that surround this face. And each of the bond here, one is perpendicular to this one. This one is perpendicular to this one, okay? Is it clear? So the bonds that have the same label are perpendicular to one another from one figure to another figure. You can also rotate to make them parallel, but here we just choose a convention to make it perpendicular. Yes?
What about the zero? The zero is like
zero is the outside face.
outside face?
Yes, zero is the face that is outside. You mean which node it maps to?
Okay, so I thought there was no reciprocal diagram for the node, but there's a zero in the middle. It's why I was thinking.
Right, this zero is the face outside, and it maps to this node here. Yeah.
Is there any information about the geometry, or this is just about the topology of the lattice? Like, how do you decide the size of your edges and
yeah,
the
that's what I'm going to say next. You construct that from states of self-stress, actually. So what Maxwell showed is that this kind of reciprocal diagram don't always exist. You only have that when you have states of self-stress. So you can actually take a state of self-stress, which is actually how I draw this network. I use red and green to denote compression and stretching. So the total force on every site is 0. So for example, this site 1 has stretching on 7 and 12, and then pushing from 1. They add up to 0. You have 3 vectors that add up to 0, okay? And then you take those 3 vectors and make a triangle, which is this one here. They are guaranteed to close because the total force is 0. Any questions? Yes?
If I demonstrate that this analogy exists, can I be sure that exists an analogy for the topological number, a topological index, if in the original lattice there is a topological index?
Yeah, you're jumping ahead.
No.
We haven't got there yet. You can later show that if 2 lattices are reciprocal to one another, they have opposite topological polarization.
But the way that I calculate this is different. And
right, so we do not have a mathematical way to show that their Q and C matrices are related, and that gives you the topological polarization opposite. There should be a way to do it. We haven't established it yet. Okay? Okay, so we see that this is a mutual relation. This one has a state of self-stress. You can use that to construct this diagram geometrically. And this one has a state of self-stress. You get this one. Okay? And this is actually a concept that has been used for a while in soft matter physics to study disordered networks, actually. So the first paper I know is this paper here, where they start from, so basically the argument is the following. When you have a granular packing, there can be multiple states of self-stress. So if it is over-constrained system, you have multiple states of self-stress. So when you only know the boundary stress, you don't necessarily know what's happening in the middle, right? If we know perfectly what are the force displacement relations of every element, you know. But in a real experimental system, you sometimes don't know. So that's basically the so-called Edwards ensemble. You know boundary stress, but the internal stress distribution, you don't know. And here the authors proposed that, for example, you start from a triangular lattice, you have many states of self-stress. Each of the state of self-stress maps to a tiling like this. And you can use the ensemble of all of these states of self-stress to write theories for granular matter, basically. And here is another work, I think, from this paper, where they take actual packings of frictional particles, and in this case, I think this is a numerical experiment, so they know what exactly are the forces between the particles. And then they can take that to construct the reciprocal diagram. In the paper, I think it is called force tiling. It's a really beautiful geometric representation of the interactions between these particles. Again, you take the stresses, you know the total force on every particle add up to 0. Each particle corresponds to a phase here. And then you can use that to make a statistical mechanics in this reciprocal space. Okay? And here is another interesting paper where they studied networks of cells with active stress. And they show that the active stress of the cells can also be represented using this triangulation, which helps you analyze the force balance on these active networks. So the basic idea here is that when you use this in soft matter problem is that when you have a network that can carry stress, that means you must have a state of self-stress there. Right? Then when you have a state of self-stress, you are able to construct such a force network. Then you can use that as a tool to analyze the properties and to write statistical mechanics. Okay? There was a question. Yes?
So I know that in 3D, the dual of the Voronoi tessellation is a Delaunay triangulation. I was wondering, so there's an energy functional that we can associate with the Voronoi tiling. Can we make a transform? Do you know if we can make a transform to the Delaunay space of the energy functional?
Oh, you mean write some kind of energy functional in the reciprocal space?
Do you think it's possible in the same way?
So the energy itself, if you, for example, look at this case, right? It is just the length squared. You sum the length squared if these are just springs. If it's a more complex energy functional, I think you should still be able to write it in the reciprocal space. Okay. Because the length here are the forces here.
As in, is the triangulation unique? As in, is there
if you have multiple, so each state of self-stress gives you a triangulation. But the reciprocal of a given network, if you have multiple states of self-stress, is not unique. That's actually, I'm going to talk about that next.
Okay, thank you.
Okay? Okay, so here, just take a little bit of detour to talk about sort of the importance of states of self-stress and what it means when something is rigid, right? So there are, because people have been studying mechanical stability in soft matter for a very long time, sometimes we still use different definitions for mechanical stability, right? One common criterion people use is no floppy modes. If you have no free moving parts, you say something is stable. However, practically, there are often other criteria. For example, if a system can carry a certain type of load, you can also say that's stable, right? You can still have moving parts somewhere. As long as macroscopically you can carry that load, then it is stable. But you can define stability in terms of different types of load. You can see whether it carries a shear, whether it carries a compression. They don't necessarily overlap with one another. So the logic is basically when you have no floppy modes anywhere, then you can carry all loads. But when you can carry one type of load, you don't necessarily carry other types of loads. So using the simple example, you can make figures like this. For example, this one doesn't have any floppy modes. It can carry any load. Here, you can carry, here I think I made it too complex. It can carry any load. And in this case, you have a network that can carry this particular load, but you have floppy modes somewhere. And then it cannot carry other types of load. So why is this relevant for soft matter, right? So you can think about generic materials. How does it go from floppy to rigid, right? you can use these different criteria. You can say when floppy modes vanish, you have stability. You can say when you have state of self-stress, you have stability. Or you define it macroscopically. You say I need an elastic modulus. In general, they don't overlap with one another, right? But jamming of frictionless soft spheres of one-sided potential is a very special case where these different criteria coincide at one point. You have a very unique point, which is right at isostaticity, where all of the floppy modes go away. First, the state of self-stress emerge. But generic materials, you have them happening at different points, okay? So I just want to sort of mention that point to show the complexity of rigidity behavior itself. Okay, so now coming back to this duality theorem, right? So how do we prove there is a one-to-one correspondence? I think I'm almost running out of time. We should be able to just do this one. So what happens is that you first take one network with two states of self-stress. This is a proof, right? You imagine you have two states of self-stress. And each of the state of self-stress, you can use it to construct a reciprocal diagram, right? Because for one state of self-stress, you know what the lengths are. You can use that to construct it. And then you ask, what is the relation between these two reciprocal diagrams that are both due to this one? It is obvious that they have different geometry. However, because each bond here, the corresponding bond here, they must be parallel because they are both perpendicular to some bond here, right? So as a result, from this one to this one, you need an irrotational mode, a mode that only changes the length of the bond without rotating them, okay? And that is this green arrow. And then from that irrotational mode, you can locally rotate each of the displacement vector by 90 degrees. You get a floppy mode, right? Because this mode only rotates the bond without changing the length. So this tells you that when I have a state of self-stress here, it gives me, so if I identify this pair as the reciprocal diagram I have, then whenever I have a state of self-stress in this one, I must have a zero mode here. There is a one-to-one correspondence you can rigorously construct, okay? So that's basically this theorem that was, I think, first appeared in this paper here and then sort of known in the mathematical rigidity, combinatoric rigidity community and engineers, but somehow was not known to physicists for a long time. So then we use this rigidity. I'm going to be just going pretty fast here. We can do it on periodic lattices. You can show that for periodic lattices, there is actually a very interesting subtlety in terms of the q equal to 0 at 0 momentum point. You need to be careful with that. And if you do all the proof, you will see that their topological polarization must be opposite to one another, which comes from the fact that you have a zero mode in one lattice here that gives you a state of self-stress in the other lattice. Sorry. If you have a zero mode for lattice A, and then that gives you a state of self-stress for the reciprocal lattice, okay? And then now coming back finally to the Penrose tiling, you can show that if you don't do anything, you have these zero modes that are bulk modes. Then, following this mechanical duality, you can copy what you did with fiber networks, right? We know it's going to polarize fiber networks. But do it on the Penrose tiling, which means you rotate each of the bonds a little bit in a coherent way. That polarizes this mode. And then we show that if you follow this rule and do these little geometric changes to the Penrose tiling, it's a very tiny change you need to do. You almost cannot tell. But then when you calculate the zero modes, it becomes polarized. Okay? What is unique here is that in contrast to the disordered networks, here I actually have long-range order. Right? The disordered networks, I don't have long-range order. I only have this polarization at the fiber level. Here, because I have long-range order, I can actually define a bulk topological polarization. And now what is different here is that I can have bulk topological polarization follow any symmetry I want to choose. I'm not limited by the choice of the crystals. Okay? And this we propose can be useful for something like if you want to build a waveguide of any peculiar shape. You can use quasicrystals because you can choose your quasicrystal lattice directions to follow any path. And then you get a waveguide like this, or you get a stress focusing device where you can program the stress to go anywhere. I think that is basically all the content I have for here. So let me see. Yeah, that's all of it. I just did it in a weird order. OK, any questions?
Go on.
Yeah. So if I understand, you have these modes that are localized along lines, and somehow you have this scheme to polarize them, right, and to make them exponentially decaying, right?
Yes.
What's the rule of thumb to do that, like to perturb these, line modes, such that you get this, such that you polarize them?
You mean for disordered system?
Yeah. Or even
for
any
fiber
system,
networks, we know. So if all of the sites are 4-coordinated, you just need to follow this table. Let me see. You just need to follow this table. That locally, if something like this, you know the mode becomes smaller. And these ways are becoming bigger.
But for the quasicrystals, it's similar, right? Or,
yes, for quasicrystals, it's actually similar. But for a generic network, for example, if you give me a jammed packing, we don't know how to do it yet.
Yeah, so but for any network that has these modes along lines, then you have...
Right,
you
if I can associate it with lines, basically.
Yeah, but then can you maybe explain in more intuitively, like what is the rationale that makes you come up to that table, for instance? Like what is it, the constraints that you try to maintain, for instance, or like how do you get to that table, basically?
Oh, this table is calculated using the transfer matrix. So you take the transfer matrix, you do a perturbative expansion for small deflection. Then you get this.
So for the quasicrystal, you did the same. You defined the transfer matrix, and then you also...
So basically, it's like after you do this for a while, you don't actually need to calculate the transfer matrix. You just look at the geometry you basically know. Because it's pretty simple geometrical rule. You just see whether the mode becomes bigger or smaller as you go from one to the next. Yeah.
So as I can understand, if you cannot, given a network, let's say the jam and packing, you cannot build the right soft mode, but you could, in principle, imagine that you can start by building the soft mode you want, and then trying to pack or to put the links and create the network you want to.
Yeah. So that is actually related to the project Jose has been working on. We started out wanted to study how to topologically polarize jammed packing. It turns out to be very difficult, but we discovered something else that was really interesting. We have not solved that problem yet. With also one of my postdoc, Ethan Stanifer, we worked very hard to try to achieve that. So anyway, so what you were saying is like you first find a mode, and then you see how you perturb that mode, right? Yeah. So I think for one given mode, we sort of know how to do it. But when you have multiple modes, right, how do you do it in a way that you have a bulk polarization that affects all of the modes at the same time? That is more difficult. Yeah.
I see.
More questions? Leandro?
Okay. For the last part of your talk, you define like a waveguide from the styling.
Yeah.
How you do that? I mean, you create like a higher dimensional network, and how you manage to, I want that kind of pattern?
Right, so there are two steps. The first step is to, that's this figure here. You first randomly draw a path, right? And then you take these sections of the path and you generate this so-called star vector. This vector is like all of these directions, you put it together, you get this star. And then you use the star to generate fiber network. So for example, I have a star like this.
So basically, you create the network.
Yeah, you create parallel lines perpendicular to each direction. Then you have the fiber network. Then you find the dual. And then you polarize it in opposite ways in this domain and this domain. Yeah.
Okay.
Can you comment on the role of topological and difference of topological robustness and topological protection in this type of problem of polarization?
So I think we usually call them, use them interchangeably, topological protection and topological robustness. Yeah.
Okay.
More questions? If not, let's thank Xiaoming for all the lectures.
Thank you.